Hello everyone, this is Dr. Nimish Kumar Srivastav, and in this module of lecture series, that means optical fiber communications, having a code of KEC 058, I am Dr. Nimish Kumar Srivastav, assistant professor in Ajay Kumar Garg Engineering College, going to discuss about what is the avalanche photodiode, what is the phenomena which is called as avalanche, what is impact ionizations, as well as we are going to discuss another important topic related to optical fiber, which is called as OTDR, which is full form is optical time domain reflectometers. It is a basic optical radar that is we are going to use in order to check what is at what distance some kind of a loss is happening in the either in the connectors, or the loss associated with the splices, or even the loss associated with the some joints. So we are going to discuss each and every things in details in this coming slide. So we will directly jump to the avalanche photodetectors. As we have already gone through what is the meaning of a photodetectors, we have discussed what is photodetector and what is the need of increasing the depletion width of the photodetectors. With all these basic knowledge, we will move to the avalanche photodiode. Now that avalanche photodiode is something which can be visualized with the help of this diagram. We are having the structure of an avalanche photodiode. That means we are having a highly doped regions on the extreme ends, and after this highly doped regions we are having a p-type regions which is slightly doped with respect to the earlier one, that is n plus, and then we are having a wider depletion region which is intrinsic regions, which is very less doped. Now in this region, as one can see, with the help of this this block, we are evaluating the we are forming a variation. We are saying that what is the variation of electric field as one move from highly doped towards the intrinsic region and then towards the extreme end of the p plus region. This n plus and p plus is indicating that these two regions are very highly doped. Now next is that as it is highly doped, this region is highly doped. Your n plus is highly doped, so we are trying to evaluate this region by drawing some dots, and after that, as this region is highly doped, that means it must be having a high concentration of electrons. So the electric field is start increasing from this side and is almost achieving a maximum value at the junction. That means like this. So we are having maximum value at the junctions because the electron concentration is very high in this region. So this electron concentration leads to a that means generation of, or leads, they are going to strike the number of another electrons in the presence of a high electric field. So as in this avalanche photodiode, we are providing a very high reverse bias. So what is happening? Whenever a photon is incidenting on avalanche photodiode, these photons going to strike the electrons, they are going to create the electron hole pair. These electron hole pair in the presence of a very high electric field going to be swept apart from each other with a very high velocity. When they are sweeping apart from each other with a high velocity, this electron going to strike with another electrons, creating a more number of electron hole pairs. I mean, if because of this photon incident, number of electrons is 2, suppose that. The number of electrons is 2 after incidenting a photon. This photon going to be swept apart with a very high velocity as within the presence of high electric field. So this high velocity electron moving with a high velocity, they are going to again strike the electron, bonded electrons. They will break the bonds and more number of electrons going to be created. These two creates 4 electrons, and that 4 electrons going to move with a very high velocity, creating another 8 electrons. So in this phase, a cumulative process is there, which leads to a high charge carrier generations, which leads to a high electric field, right? Or a high current will flow through the circuit. Now there is another term which is called as impact ionizations. Why? Because in the presence of high electric field, these electrons are attaining a very high velocity, they are impacting another electron with hitting another electron with a high velocity, breaking the bond of that electron, that charge carriers, letting the electron free. These free electrons will start moving apart from each other with a very high velocity. Constitute more number of electrons will move with a high velocity, and they will move across the junctions and across the complete materials, and they will constitute a electric current. So that's why this avalanche photodiode is there. In this region, we can see that the electric field start increasing, move to a maximum value at the junction of N plus and P. After that, it again start decreasing, because here we are having a less number of positive charge carriers. So that positive charge carriers going to decrease. Because of that, the strength of electric field is decreased and decreasing, and the moment it has reached to a portion of the intrinsic layer, here the electric field is constant because it is less doped and the number of electron equals to the number of holes. So with the less doped, the electric field will remain constant till the region of the intrinsic layer, and again that it is reaching the P plus regions, which is having a high number of holes, going to again decrease the number of electrons present in the electric field, which constituting flow of current and electric field. They further decrease to a value and may further move to a value of a 0. So in this way, the electric field is varying in the avalanche photodiode. So avalanche photodiode, the two terms that is associated with the avalanche photodiode is the name, that is avalanche. That means that there will be sudden increase in the number of electron. That is why avalanche is called as avalanche. And impact means that the number of electrons, the higher number of electrons that is let free because of the high velocity of this electrons, they are moving away from each other, so they are definitely going to hit another electrons which is bonded with the atoms, and they will let that electron free. So these freed electrons, they will move across the material through the wires and constitute a electric current. So this is the terms that is associated with the avalanche. So here we are knowing that the term reach through arises from the photodiode operations. When the low reverse bias voltage is applied, most of the potential drop is across the P N plus junction, and the depletion layer widens with increasing bias until a certain voltage is reached, at which the peak electric field at the P N plus region or junction is about 5 to 10% below that need which is required to have the avalanche breakdown. At this point, what will happen? The depletion layer just reaches through to the nearly intrinsic N plus region. So that's why it is called as a reach through junction diode. Now next point associated with this is that avalanche photodiode constructed of a material in which one type of a carrier largely dominates impact ionization, exhibits low noise and large gain bandwidth product. So this is the main important advantage of your avalanche photodiode. Now the next thing is that, as we have understood that that there is a charge carrier multiplication that is taking place inside the avalanche photodiode. So that means we have to find the terms which is called as we have to know the value of some multiplication factor, because the indirectly charge is getting multiplied, right? Because we have increased the number of charge carriers by providing a very high electric field, by increasing the width of the depletion layer. So we have to just formalize that concept, that what is the factor with which a charge is getting added up or the charge is getting multiplied. So we are going to find the multiplication factor M for all charge carrier generated in the photodiode, which is given by the formula Im upon Ip. Now what is the term? Im is the average value of the multiplied output current, and Ip is the unmultiplied photocurrent, right? Ip is the unmultiplied photocurrent, which is given by this formula. Ip equals to Q upon H nu P in 1 minus e to the power minus alpha j into omega, right? Where alpha j is the absorption coefficient. Now, so with this formula, there are few formulas that one have to keep in his mind when he is studying or when he is attempting his semester exam. Formulas that is associated are what is absorption coefficient, then what is responsivity, what is quantum efficiency of photodetector, and as well as what is the quantum efficiency of pin photodetector, and what is the responsivity. Similarly, if we are moving to avalanche photodetector, what is the term that we have to keep in our mind is the multiplication factor or M. So we have to keep all these things in our mind whenever we are trying to attempt for a semester. So the term, the numerical can be directly asked in the exam. They are not going to ask just the numerical based upon this topic. They will ask the numericals by adding that numerical inside a broad question, will be something like explain the phenomena of a reach through in the avalanche photodiode, or they will ask that how the electric field is varying inside the avalanche photodetector, or they are going to explain the impact ionization in a APD. So after explaining that thing with the proper diagram, block diagram, as well as the electric field variation, one have to remember this formula also, or they have to write this formula also supporting the answer of explanation, and in that also they are going to ask you a small numerical based of 1.5 or 2 marks, like silicon or given silicon avalanche photodiode has a quantum efficiency of 65% at a wavelength 900 nanometer, and they are saying that the 0.5 microwatt of optical power produces a photo multiplied photocurrent or multiplied photocurrent of 10 microamp, and they are asking that find the multiplication factor. Now these are the numericals that one can easily find in a book, that means senior for optical communications. This is a very standard book, and one can easily get a solid concept, build the solid concept based upon that book. So this is a very important formula. So one can easily write the formula IP is equal to RP in, where R is your responsivity. From this you can find the value of IP, that means photocurrent, and after getting the photocurrent you can directly put the value of a IP in the multiplication factor M, because M is equal to IM upon IP. IM is the average value of a total multiplied or output current. So from here you can directly get the value of a M as 43. That means the primary photocurrent is multiplied by a factor of 43 with the help of avalanche photodiode. That means we are getting an enhanced value of a photocurrent. Now the next thing is another important formula associated with the avalanche photodiode is analogous to the pinned photodiode also, the performance of a APD, which can be characterized by its responsivity given by a formula RAPD equals to NQ upon H nu, or eta q upon H nu into M, where this eta q upon H nu is your responsivity of the pin photodiode, or responsivity of a photodetectors, normal photodetectors. So as we are using the word avalanche photodiode, so there will be some enhanced performance, there will be some enhanced responsivity, there will be some enhanced photocurrent, that means there. So we have to find that value. So responsivity of the photodiode APD can be written as R into M. So RAPD is equal to R into M. R is the unity gain responsivity, right? So this is the all associated terms with the avalanche photodiode, and the next thing is about the optical radar, that we will discuss in detail in our next video lecture. And before winding up this thing about your photodetectors, let us take a brief overview about photodetectors. So we have discussed in today's class about the photodetectors, that means what is the basic operations function of your photodetector. We know that photodetector is used for converting a photocurrent or optical energy into a electrical energy, or we can say that optical electric field into a current or into a electric field, right? Optical signal into a electrical signal. So that is the photodetector. Now once we got this, that it is used for some conversion, that means converting a optical signal into a electrical signal. Now after that we have to understood that that means what is the basic principle of a photo detector is that as most of the photon is incidenting in the depletion region, this depletion regions generating the electron hole pair, and if we are swifting apart that electron hole pair by providing a biasing opposite to with respect to that charge carrier, like your p side is having a hole as a majority charge carrier, so connect that p side with the negative terminal of your battery, and electron is having, and the n side is having an electron as the majority charge carrier, connect a positive terminal with the n material. So what will happen? You are provide reverse bias this junction, reverse bias this diode. So with the reverse biased, the depletion width also increased, right? And if the depletion width increase, the photon incidenting on the depletion layer going to increase the number of electron hole pair. This increased number of electron hole pair going to be swept apart with the help of attraction force, that is attracting the hole towards the n terminal and electron towards the p terminal. So as a result of that, they will start flowing and a closed loop will be formed and the electric current will start flowing. Now this was the very basic concept associated with the photodetector. Now similarly, if once got that this information that this is the basic way in which a photodetector operates, now he should concentrate on increasing the performance of this photodetector. How he can increase the performance? We know that photon is incidenting in the depletion region, and if somehow we are expanding the depletion region, so we are expanding, if the depletion region is expanded, so that means the photon, more number of photons going to incident on that region. So if the number of photons striking that depletion width is increased, then what will happen? More number of electron hole pair will be created, and if we are again sweeping apart those electron hole pair, we are creating a electric current inside the circuit. Now that leads to a generation of the idea of a pin photodetector, in which the two materials are there, p type and n type, and between these two we have created a high width intrinsic layer, so that depletion width is increased because of the reverse bias, and the more number, as we have intentionally increased the width of the intrinsic layer, so that means as a result of that, more number of photon will incident and it will let the electron free, creating a generation of electron hole pair generation, right? So with this we have somehow increased the performance of the earlier the basic was p-n junction photodiode. Now with the creation of a pin diode, we have increased the performance by increasing the performance. How? We have sandwiched the intrinsic region between the p type and n type. Now after that, again we want to increase the performance of this pin diode also further. So this pin diode for performance can be further increased by using a avalanche photodiode. Somehow create more number of electron hole pair. Earlier we have created the more number of electron pair by increasing the width. Now we are creating the more number of electron hole pair by applying a high reverse bias, right? We have applied a very high reverse bias inside the avalanche photo detector. Now this high reverse bias, what will happen? Going to increase, obviously it will increase the width, but what will happen, that in the, if the more number of photon is incidenting in the depletion regions, which leads to a creation of electron hole pair, these electron will strike, they will start moving away from each other, electron hole, they will start moving away from each other, and they will be attracted towards the opposite polarity battery. So as that strength is very high, So the force with which they are moving away from each other, swept apart and moving away from the junction, that force is very high. So that means they will start moving with a very high velocity. So when they are moving with a very high velocity, electron is moving with a very high velocity, it is definitely going to strike the another electron with a very high velocity, leading to, or they will let free that electron which is already bonded with the atoms. It will get free, and it will also start moving with that high velocity. But because if something is striking you with a very high velocity, you will also start moving with that velocity, obviously. And that velocity is also further increased in the presence of a high electric field, which is high electric force which is applied, or high biasing voltage which is applied. So that leads to a creation of more and more charge carriers. So there will be a avalanche type phenomenon that is going to occur. That means there will be sudden increase in the electric field. A very high electric field will be there will be high electric current will moving through the circuitry. So with this knowledge, we will going to end this topic of a photodetectors. We have gone through all the parameters associated with that. We have discussed some numerical and what is the pros and cons on some basic photodetectors. And after this, in our next video lecture, we will discuss about one of the most important testing equipment that one optical engineer are using right nowadays is OTDR, that is optical time domain reflectometer. So in our next class, we will discuss in detail the basic principle of that OTDR. So thank you all. We will meet in our next lecture.